equations. Okay, so let's go to our first content block now. So integration. In the January lecture series, if you went to the January lectures, Krisha covered how to do integration in her Maths Advanced lecture, and I covered the foundational material for Extension 1 integration in my Maths Extension 1 lecture. So today we'll be moving on, and I'll be covering how to do integration by substitution with both definite and indefinite integrals, how to integrate sine squared x and cosine squared x, as well as integrals involving inverse trigonometric results, as well as how to find the area between two curves. So let's talk about integration by substitution first. So you might often hear integration by substitution being called U substitution. U in this case is a variable which we let equal to some part of the expression we're given to integrate. And when do we need to do this? Well, basically integration by substitution allows us to basically simplify a more complex integral into a simpler integral that is easier to solve. So just keep in mind, you don't always need to use U. By convention, it is U, but sometimes you might use like a different variable like theta instead, or something like that. So luckily in Extension 1, the question will always tell you when to use integration by substitution. So you will basically be told, use this particular substitution, and then you'll be able to just apply it to solve the integral. Unlike, of course, if you do Extension 2, they actually don't necessarily always give you the integral. You'll just be expected to kind of come up with the substitution yourself in some occasions. So keep in mind, if you do Extension 2, you might not always be given the substitution, whereas in Extension 1, you'll always be told, use this particular substitution. So the basic steps of how to do an integration by substitution question, you want to first of all start by differentiating the substitution, and then you want to change the integrand into an appropriate form using algebra. And in the case of if you're doing a definite integral, you want to change the limits as well. Once you've simplified everything in terms of U, you then integrate normally. And then in the fourth step, if you are working with an indefinite integral, you want to convert back to your original variable. So this is kind of complicated when you sort of write it out like that. It makes much more sense once we actually apply it to a question. So I like to mentally group integration by substitution questions into two types of questions. These aren't really formal classifications. These are just what I personally like to group them in. So we got chain rule type questions. So, or as I like to call them, dumb substitutions, because these questions can be done much more quickly using the reverse chain rule without actually needing to make a substitution. So yeah, I call them dumb substitution questions because you don't really need to use a substitution. However, if you struggle to use the reverse chain rule, obviously the substitution will make things easier for you. Although the flip side is that it is more time consuming. So it's much quicker if you just use the reverse chain rule. And then the second type are the non-chain rule type questions where the substitution is actually useful to help you solve the integral, as opposed to just being able to just do it quickly using the reverse chain rule. So let's look at reverse chain rule type questions. So before we talk about that, let's just talk about the reverse chain rule. So remember, when we differentiate anything, we have to use the chain rule and multiply by the derivative of the function inside. So that's like something you learned in year 11 when you looked at how to differentiate. If there's a function inside, you need to also differentiate the function inside and multiply on the outside when you differentiate the entire thing. So basically, if you have like a function and we got a function inside, when you differentiate this, we get, not only do you just differentiate the outside like normal, but because it's a function inside, you also need to multiply with the derivative of the thing inside. So this is the normal chain rule. So that's what happens when you differentiate. But remember that integration is the opposite of differentiation, and it basically reverses what we've done with differentiation. So in order to reverse the process when you're integrating, if there's a function inside a function, you want to make sure that the derivative of the function inside is already being multiplied on the outside before we can integrate the whole thing. So this is known as the reverse chain rule. So basically, in other words, if you have a function, let's say you've got g of f of x, and there's a function inside, in this case, we've got f of x, you want to make sure that the derivative of the thing inside is already on the outside before you can then proceed to integrate this entire thing normally. And this accounts for the fact that, let's just say we wanted to differentiate this, we would get the derivative, but then we'd need to multiply by the derivative of the function inside. So that's what happens when you differentiate. But when you integrate, you want to make sure it's already in this particular form where the derivative of the thing inside is already on the outside before you can then proceed to integrate the entire thing. So it's basically just counteracting the chain rule, hence why it's called the reverse chain rule. So this is a really important principle you need to know when you integrate, because it applies for all functions. It doesn't matter what function we're working with. It doesn't matter if it's exponential, trigonometric, or just out like a normal like x to the power of n or something like that. It doesn't not matter. You need to make sure you are accounting for the reverse chain rule. Okay, so now let's go through some worked examples illustrating the chain rule type question. So let's just say we want to integrate x plus 2 times x squared plus 4x plus 1 to the power of 4. And we're told to use the substitution u equals x squared plus 4x plus 1. So the first step is you want to differentiate your substitution. So obviously here we're told to use the substitution u equals x squared plus 4x plus 1. So the first step is you want to differentiate u with respect to x. So we're differentiating the substitution. So in this case, the derivative of that is going to be 2x plus 4. Actually, this color is a bit hard to see maybe, so I might change the color. Maybe, yeah, that's much easier for you to see. So, yeah, we differentiated it. So, yeah, you have your substitution, then you differentiate the substitution. So I'm going to differentiate it with respect to x. So we got 2x plus 4. And now, for the purposes of the HSC, you can sort of treat derivatives like fractions. So what I'm going to do is I'm going to take the dx to the other side. So I'm going to say 2x plus 4 dx is equal to du. Now, the next step is we want to rewrite this entire integral in terms of u. So I can see that the x squared plus 4x plus 1, this thing inside, will just simply become a u. But I want to make sure I convert all the x's in terms of u. So I see here I have an x plus 2 dx. But here I have a 2x plus 4 dx. But I want an x plus 2 dx. But what I can see is I can divide both sides by 2. So I can say that du divided by 2 is just going to be x plus 2 dx. So now I got an x plus 2 dx. So I'm going to convert the integral all in terms of u now. So this thing is equal to the thing inside this here is u, so it's going to be u to the power 4, and the the x plus 2 dx here becomes the u over 2. So I can take the half to the front of the integral. So we got this, and now I can integrate it like normal. So this will become half times u to the power 5 over 5. Don't forget your plus c because it's an indefinite integral. But the thing is, I can't just leave it like this because this is in terms of u. I need to convert back in terms of x. So I'm going to say this is going to be 1 over 10. The u is going to be x squared plus 4x plus 1 to the power of 5. U squared x squared plus 4x plus 1. And then I got the plus c. So this is my final answer for this integral. And you can see u to the power 4 is much easier to integrate than this entire thing. So yeah, that's how we basically do an integration by substitution question. You have your substitution, you differentiate, you rearrange to make all the x's in terms of u, and then you proceed to integrate like normal. Then remember, if it's an indefinite integral, like it was in this case, you want to make sure you convert back to the original variable. Okay, so this is part B. So we're told to evaluate this integral now without a substitution, just using the reverse chain rule instead. So this is a chain rule type question because you could have done this question without a substitution. So here we have a function inside another function. So inside the function here, we got x squared plus 4x plus 1. Now, with the reverse chain rule, if we have a function inside a function, we want to make sure that the derivative of the function inside is multiplied on the outside. So in this case, the derivative of x squared plus 4x plus 1 is 2x plus 4. So we want to make sure we got a 2x plus 4 on the outside. However, we don't have that. So we're going to have to do some bit of algebraic manipulation in order to get that to happen. So this is our integral. So I want a 2x plus 4 on the outside, but we don't have that. But what happens if I just multiply by 2? If I multiply this by 2, I'll get 2x plus 4 when I expand the brackets. But I can't just randomly multiply it by 2 because I'm changing the question. I don't want that to happen. So what's going to happen? What can I do to counteract that? Well, I can balance it out by dividing by 2 on the outside. So you can see here, what I've done is I've divided by 2 and multiplied 2 by 2 at once. So these things actually cancel. So I haven't actually changed the question. I've just simply done a bit of manipulation so that I can have a 2x plus 4 here. So yeah, this thing will become 2x plus 4 once you expand the brackets. And now this is in the perfect form where the derivative of the thing inside is being multiplied on the outside. So now I can just integrate this entire thing like normal. So raise the power by 1 and divide by the new power. So this will be half times x squared plus 4x plus 1 to the power of 5 divided by 5, which is going to be 1 over 10 x squared plus 4x plus 1 to the power of 5 plus c, because you don't want to forget your arbitrary constant when it's an indefinite integral. So you can see we got the exact same answer, but here we actually didn't need to use a substitution, which saves time because it's going to be less time consuming. So let's look at a second type now of a this is a non-chain rule type question. So this one you can't use the reverse chain rule to just directly do. This one, the substitution is actually useful. So we're told to evaluate x times square root of x minus 4 with respect to x using the substitution u equals x minus 4. So just like before, in extension 1, you're always given the substitution. So I'm going to let u equal x minus 4. So now what I can do is I'm going to differentiate the substitution. And then the derivative of x minus 4 is simply just going to be 1. So I can say that du equals dx, like so. And now my next step is to rearrange this integral and make all of the x's in terms of u. So what I can do here is inside the square root, the x minus 4 just becomes a u, but for the x, I can actually rearrange this so that I can say that x is going to be u plus 4. If I take the 4 to the other side and make x a subject. So here, this integral of x root x minus 4 dx, I'm going to convert all of these in terms of u. So x becomes a u plus 4, and the x minus 4 becomes a u, and dx just becomes du, because we said du is equal to dx. So this will become du. So now I can proceed to expand. So this will, square root of u is just u to the power of half. So when I expand, this will be u to the power of 3 over 2 plus 4 times u to the power of half du. So now when I integrate that, it will become u to the power 5 over 2 divided by 5 over 2, because I raised the power by 1, divided by the new power, plus 4 times u to the power 3 over 2 divided by 3 over 2. So this will become 2 over 5 u to the power 5 over 2 plus 4 times 2 over 3, which is going to be 8 over 3 u to the power 3 over 2 plus c. But I can't just leave my answer like that. Remember that u is equal to x minus 4, so I need to convert everything back in terms of x minus 4. So this will be 2 over 5 x minus 4 to the power of 5 over 2 plus 8 over 3 x minus 4 to the power of 3 over 2 plus c. And that is how we do a question like this. And in this case, you couldn't actually use the reverse chain rule to do this question. So this substitution is actually useful in this case. Although there is ways to do this integral without needing to use a substitution, using clever algebra as well. I'm not going to go into it today, but if you are curious, try brainstorming a way you can do it. But there is ways of doing it, and I know how to do it, but I'm just not going to go into it right now in the purpose of saving time. Okay, so let's have a look at another question. This one was actually a past HSC question in the 2008 HSC. So the question is that we're going to use the substitution u equals log base e x, so ln x, to evaluate this definite integral. So if you want, you can just pause this video right now and go ahead and try doing it. To see if you could get it by yourself. But if you want to go through it, we're just going to go through it now. So this is the integral we're told to do, and we're told to use the substitution u equals ln x. So the way we do it this time, this is a definite integral. So there is an extra step we need to account for, which I'm going to point out when we do it. So we are told to use the substitution u equals l log base ex, so that's ln x. So when I differentiate that, so yeah, I'm just gonna, since the question uses log base ex, I'm gonna do it like that. So the derivative of log base ex is just going to be 1 over x, if you recall from when you learned how to differentiate ln x, differentiate logarithms. So therefore, I can say that du is equal to 1 over x dx, like that. And since this is a definite integral, I'm going to want to remember to change our limits. So I'm going to draw up this little table. So this is u, so this is x, and this is u. So our original limits were, we're integrating from e to the power e squared. And the way I'm going to find what our new limits is we're going to simply take the substitution and plug in our value for x to see what our new value of u is. So when e is equal to, when x is equal to e, log base e is just simply going to be 1. And when x is equal to e squared, log base e squared is simply going to be 2. So our new limits are from 1 to 2. So now we can say for this integral, that's equal to, if I have my new limits from 1 to 2, the 1 over x here, the 1 over x dx becomes a du, because 1 over x dx is du, so we got that. And now I just got 1 over log base ex squared, so that's just going to be 1 over u squared, like that, because u is equal to log base e squared. So this is the same thing as integrating u to the power of negative 2 from 1 to 2. So this will become u to the power of negative 1 over negative 1 from 1 to 2. And when I evaluate the limits, that's going to be, oh yeah, this is just negative 1 over u from 1 to 2. This is going to be negative half minus 1 over 1, which is negative half plus 1, which is going to be half. So our integral from our integral of 1 over x log base ex squared from e to e squared is going to be half. And in this case, this question is actually a chain rule type question, because you could have done this without having to use a substitution, because notice that there's a function here, and the function inside the function derivative is already being multiplied on the outside. So in this case, you could have done this without a substitution quite easily. Okay, here, okay, so we got another question now, and this is from the 2017 HSC paper. So we're told to integrate x over root x plus 1 from 0 to 3 using the substitution x equals u squared minus 1. So here, this is a non-chain rule type question, because this one, the substitution is actually useful for, because we can't just use the reverse chain rule directly, although there is a way of course, just doing this integral without a substitution. But yeah, we can't just directly use the reverse chain rule, so the substitution here is actually useful. So again, if you want to try this question yourself, you can pause this video and go ahead and attempt it, but we're going to go through it now. So I'm going to change the color so it's easier to see on this white screen. So again, same steps. We're going to, this time, the difference is x is the subject rather than u. So we're going to just use the substitution that the question tells us to do. So we're going to let x equal u squared minus 1. So I'm going to differentiate the substitution. So this time I'm differentiating x with respect to u. So this will become 2u, yeah, it's just going to be 2u when I differentiate x with respect to u. So now I can say dx is simply just going to be 2u du. So just dx simply will just become dx. It will simply become 2u du. And again, this is a definite integral. So what I'm going to do is I'm going to make sure I change the limits. So my original limits in x were from 0 to 3. And then what happens when x is equal to 0? U will become 1. So u would be plus minus 1 normally, but for definite integrals, you don't need to worry about doing plus minus. You can just take the positive case. So it will just be 1. And when x equals 3, u squared will be 4. So therefore, u will be 2. So our new limits are from 1 to 2. So now this integral will become, our new limits are from 1 to 2. Here, x at the top becomes u squared minus 1. And at the bottom, we got root x is just u squared minus 1 plus 1. And the dx, well, that becomes 2u du. Like that. So when I simplify, what actually happens is this is u squared minus 1. Here, u squared minus 1 plus 1 will just be the square root of u squared. So it will just be u here. And this u cancels out with that u. So we actually get, if I take the 2 to the front, 2 integral from 1 to 2 of u squared minus 1 du. And this, you can see, is much easier to integrate compared to integrating this directly. So this will become 2, when I integrate, it will be u to the power of 3 over 3 minus u from 1 to 2. So I'll just plug in the limits now, and remember to be really careful when you do that. 8 over 3 minus 2, and don't forget to keep everything in brackets. So it will be minus 1 over 3 minus 1. like that. So this will be 8 over 3 minus 2, which is 2 over 3, minus a third minus 1, which is minus 2/3. So this will become 2 times 4 over 3, which is 8 over 3. So our answer in this case for this integral is 8 over 3. So you can see, same steps with integration. You just want to make sure you change the limits and convert all the x's into u's at the same time.